Next heading is torque on an electric dipole in a uniform electric field. As you know, the difference between uniform and non-uniform electric fields. If the magnitude and the direction of the electric fields are the same at various points in an electric field, then the field is said to be a uniform electric field. If the magnitude and direction differ at different points in an electric field, then the field is said to be non-uniform electric field. How will you represent a uniform electric field? A uniform electric field is generally represented by parallel lines. These are all uniform electric fields. The separation will be the same. This is a representation for uniform electric field. Magnitude of electric field at various points. I can say A, B, C, D. Whatever the point I assume, the magnitudes of electric field will be the same. The directions of electric fields are also the same. So we can say such fields are said to be uniform electric fields. We are going to calculate the torque acting on an electric dipole in a uniform electric field. What is the necessity of speaking about torque? About torque on a dipole in a uniform electric field? We can have a simple explanation here. Suppose you are sitting nearby a flowing river. You happen to throw a wooden log into the river. What will happen? You are throwing it perpendicularly through the flowing water. Water is flowing. You are throwing a wooden log perpendicular to it. What will happen? The flowing water will turn out the wooden log along its direction of flow. In the same way, and how it happens? It is because of the torque produced on the wooden log. How torque is produced? Two forces will be acting on the ends of the wooden log, which will bring out a rotational force on the wooden log, which will make the wooden log to turn along the direction of the electric field. So it will tend to move, it will turn around, it will align along the direction of the flowing water, and then it will tend to move along the flow of direction of water. In the same way, if you consider an electric dipole in an uniform electric field, you can say here a charge minus q at A and another charge plus q at B. An electric dipole is placed. This is the midpoint O. The separation between the two charges is 2A. I can mark this as A and A respectively. As you know very well, these two charges are existing in a uniform electric field. So this plus charge plus Q charge will experience a force F vector equals plus Q into E vector. So one force which is acting on the charge plus Q will be acting along the direction of the electric field, and another force F vector equals minus of Q into E vector is the force which acts in a direction opposite to that of the direction of an external electric field, and the two forces are equal in magnitude and opposite in direction. So the net force acting on the dipole is 0. See, the two forces, F vector is plus Q into E vector and this one is minus Q into E vector. The electric fields at various points have the same magnitude. So the forces exerted on them have the same magnitude, but they are acting on different directions. So the net force acting on the dipole is 0. But the forces are acting along different lines of actions. Different lines of actions. So they are separated by a perpendicular distance. They are separated by a perpendicular distance. We can say here the dipole is making an angle theta with respect to the electric field, and the two forces are not acting along the same line. They are acting along different lines of actions, and they are kept separated by some distance. So the perpendicular distance of separation can be represented as 2a sin theta. We can say here now, though the net force acting on the dipole is 0, because of the two forces which are acting along different lines of actions separated by a perpendicular distance 2a sin theta, we can say here there will be a net torque. There will be a net torque. So a torque will be acting, a net torque will be acting on the dipole. Net torque will be acting on the dipole. What will happen if the torque acts on the dipole? The torque makes the dipole to align along the field direction. It will rotate the dipole to align along the field direction. What will be the magnitude of torque acting on the dipole existing in an electric field? We can say here the expression for net torque can be given as tau net vector is equal to, or the torque about the point O. We are going to speak about the torque about the point O. The net torque about the point O is given by OA vector multiplied by minus of Q into E vector plus OB vector multiplied by Q into E vector. Actually, this is a cross product. As you know very well, the torque is expressed by tau vector equals R vector cross F vector. Tau equals R cross F. So about the point O, I am calculating the net torque produced by the two forces. So what I am doing is, I am taking the distance of one force from the point O as OA and the force whose magnitude is minus QE vector. I am taking R vector cross F vector. This will give you one torque. And this force multiplied by this distance will give you another torque. If these two torques are added up, then they will give you the net torque. So the net torque tau net is equal to OA vector cross minus of Q into E vector. And at the same point O, due to the charge plus Q, force acting on the charge plus Q, the torque is OB vector cross Q into E vector. So the net torque can be given out by the expression as OA vector cross minus Q into E vector plus OB vector cross Q into E vector. And the torque will act in a direction perpendicular to the plane of the diagram inwards. This is by curl of a vector. Or otherwise you can say, if you take the cross product of two vectors, the resultant of the two vectors will act in a direction perpendicular to the plane containing the other two vectors. This is the right-handed rotation of vectors. So we can say here, if A vector and B vector are acting by making some angle theta, then C vector is equal to A vector cross B vector. And how can we write this C vector equals A vector cross B vector? In order to find out the direction of the resultant vector, you have to move A vector towards B vector through its smallest angle. You have to rotate A vector towards B vector, where the thumb is projecting up. Thumb is projecting in the upward direction. So the resultant vector will be acting in a direction perpendicular to the plane containing the two vectors. A and B are in one plane. A and B are in one plane. A moves towards B. As you rotate A towards B through its smallest angle, then the thumb will be projecting in the upward direction. That gives you the direction of C vector equals A vector cross B vector. In the same way, if you calculate the torque, net torque acting on the dipole, actually dipole moment will be acting along this direction. P vector will act from minus Q to plus Q. We are going to bring out the expression first. From that, we can explain how the torque acts perpendicular to the plane of the diagram inwards. Any field which acts, or any quantity which acts perpendicular to the plane of the diagram inwards is represented by a circle with a cross. So I have represented a circle with a cross, which indicates that the torque acts perpendicular to the plane of the board inwards. Fine. The magnitude of torque is tau net vector is equal to cross product of two vectors, OA vector cross minus Q into E vector. A vector cross B vector is AB sin theta. Modulus of OA vector, modulus of minus of Q into E vector into sin theta plus modulus of OB vector, modulus of Q into E vector into sin theta. What is OA vector? A. OB vector? A. So instead of OA vector, I can write A. Magnitude of this one, so Q into E sin theta plus OB is also A, Q into E sin theta. I am speaking about the magnitude alone. So 2A Q E sin theta when you sum up. 2A into Q is nothing but P. So I can write this as P into sin theta. This is tau net. So the magnitude of the torque can be given by the expression tau equals P sin theta, since P equals 2A into Q. The product of magnitude of any one of the charge and distance of separation between the two charges is dipole moment. So 2A into Q is replaced as P, electric field is E sin of theta. So net torque is tau equals P into sin theta. If you want to represent this in a vector form, I can write tau net vector is equal to P vector cross E vector. Where from this is obtained? As you know, A vector cross B vector is AB sin theta. So AB sin theta is replaced as A vector cross B vector. So tau net vector equals P vector cross E vector. Now, if I consider A vector as P vector, B vector as E vector, then P vector must be rotated towards E vector through its smallest angle. Then I will get the direction of torque, the resultant vector. So C vector is nothing but torque vector. So in this diagram, if you look at the case, dipole moment acts from minus q to plus q. This is P vector. Electric field vector acts along this direction. Theta is the angle between these two. So what is theta here? Theta is the angle made by the dipole moment with respect to the uniform electric field. Theta is the angle made by the dipole moment with respect to the uniform electric field. P vector and E vector are in this particular plane. So I can rotate P vector towards E vector through its smallest angle. As I mentioned you earlier, it must be rotated through its smallest angle. That is the rule. So P vector must be rotated towards E vector through its smallest angle. My thumb is projecting inwards, so I can say that torque will act perpendicular to the plane of the board inwards. That is represented by a cross with a circle. So the torque acts perpendicular to the plane containing P vector and E vector. If P vector and E vector are lying in the plane, torque will be acting in a direction perpendicular to the plane of the board. The magnitude of torque is tau equals P sin theta. This is magnitude. And the vector form of torque is tau vector equals P vector cross E vector. From this magnitude of torque, we can speak about the different values of torque at different positions of the dipole. When do we say the torque is maximum? Torque is maximum when theta equals 90 degree, which means if the dipole is perpendicular to the uniform electric field, theta will be equal to 0. Electric field minus q plus q, this is F vector plus, this one is F vector minus, which means the forces are acting on these two charges. The angle between the electric field and the dipole moment minus q2 plus q is 90 degree. If theta equals 90 degree, sin 90 is 1, tau equals P, so torque is maximum. So maximum torque will be obtained when theta equals 90 degree, which means when the dipole is aligned perpendicular to the field. So the maximum value of torque will be equal to P. Since theta equals 90, sin 90 is 1. Tau maximum is equal to P. Simply product of magnetic dipole moment, magnitude of dipole moment and the electric field. And the torque is 0 when theta equals 0 degree. That is, if the dipole is aligned parallel to the electric field. Aligned parallel to the electric field. What will happen when a torque acts on the dipole? The dipole will be rotating in the field, in the uniform electric field. So obviously the dipole will tend to align parallel to the electric field because of the action of the torque. So it aligns the dipole along the field direction. So what will happen if you represent the direction here, minus q plus q, you can say here this is the point O, dipole moment acts from minus q2 plus q. So theta made by P vector with respect to E vector is 0, sin of 0 is 0, so torque acting on the dipole is 0. So torque is maximum when the dipole is perpendicular to the electric field, and the torque is 0 when the dipole is aligned parallel to the electric field. So we can say here, if the dipole is aligned parallel to the electric field, no more torque will act on the dipole. So in this particular case, I can say the torque acting on the dipole is 0. Already we saw net force acting on the dipole is also 0. So tau net as well as F net both are 0 in this particular case. So both the dipole, both the torque as well as the net force acting on the dipole is said to be 0 when the dipole is aligned parallel to the electric field. So when the dipole is aligned parallel to the electric field, the net torque is 0, net force is also 0. In case of the dipole which is perpendicular to electric field, the torque is maximum but the net force is 0. Net force is 0, but there will be a maximum torque when the dipole is aligned perpendicular to the electric field. And we can say here this dipole, when aligned along the direction of the electric field, when it is aligned along the direction of electric field, we can say the dipole is in stable equilibrium. Dipole is in stable equilibrium. Dipole is in stable equilibrium. So shall we say the dipole is said to be in unstable equilibrium? Of course, yes. Dipole will be in a state of unstable equilibrium when the dipole is aligned to the electric field in the direction opposite to the field, minus q plus q. Dipole moment P vector is aligned opposite to the electric field. If it is the case, then theta equals 180 degree. Theta equals 180 degree. In this particular case also, torque acting on the dipole is 0, force acting on the dipole is 0. So I can consider this as third case. This is 1, this one is 2, and this one is 3. In the third case, theta equals 180 degree. We can say net torque acting on the dipole is 0, net force is 0, but the dipole is in a state of unstable equilibrium. Dipole is in a state of unstable equilibrium. What will happen if you release it? Actually this state will not be attained by the torque acting on the dipole. Actually some external agencies must make the dipole to align in a direction opposite to the electric field. If you release it, then what will happen? The dipole will once again come along the direction of the electric field. It will return back to the direction of electric field. So this is the action of torque on the dipole when placed in a uniform electric field. Suppose if the dipole is placed in a non-uniform electric field, what will happen? If the field is non-uniform, non-uniform fields are represented by this diagram, like a field line which will be moving like this. The magnitudes of field at different points will be different. If you place a dipole, minus q and plus q, see at this point I can say the electric field is E1. At this point electric field is E2. The fields themselves will differ. They have different magnitudes at different points. So if this plus q is experiencing a force, I can write F is equal to q into E2 vector, or F vector equals q into E2 vector. And at this point I can say F vector equals minus q into E1 vector. The fields themselves are different, so the forces acting on the two charges are different. Forces acting on the two charges are different. So there will be a resultant force. So F net is not equal to 0 in this particular case. And also the torque is also not 0. Net torque is also not 0. There will be a net torque due to the action of two forces at a different line of actions. So there is a different magnitudes of force. So there will be a net force acting on the dipole. Right at the same time, there will be a net torque which will be acting on the dipole. So when a dipole is placed in a non-uniform electric field, what will happen? The dipole will experience a net force as well as a net torque. When the dipole is placed in a uniform electric field, the net force acting on the dipole is 0 always. Net torque acts on the dipole, and net torque acting on the dipole differs depending upon the position of the dipole in a uniform electric field. If the dipole is aligned perpendicular to the field, net maximum torque will act, which is P, and net force is 0. When the dipole is aligned parallel to the electric field, net torque as well as net force is 0. But the dipole is said to be in a state of stable equilibrium. When the dipole is aligned anti-parallel to the field, electric field, then theta is 180, net torque and net force is 0, but dipole is said to be in a state of unstable equilibrium. An important application of torque on an electric dipole in a uniform electric field is microwave oven. How a microwave oven works? It is an important domestic application of this torque on an electric dipole in a uniform electric field. Whatever the food we cook, they always contain water molecules in it. Water molecules are permanent electric dipoles. Water molecules are permanent electric dipoles. If an oven is operated, microwave oven is operated, it produces non-uniform oscillating electric field. When the oven is switched on, oven produces a non-uniform oscillating electric field. Non-uniform oscillating electric field is nothing but a microwave. Microwave will always vary in terms of sinusoid, in the form of sinusoidal variation. So the field is said to be non-uniform. So a non-uniform oscillating electric field will be produced. In such a non-uniform oscillating electric field, a water molecule which is existing along with the food material which is to be cooked, which is a permanent electric dipole. This permanent electric dipole is placed in a non-uniform oscillating electric field. What will happen? It will be experiencing both force as well as torque. So the dipole will get excited and the dipole will be rotated in all directions. So the bond which is connecting the oxygen and hydrogen molecules possesses potential energy. When it is continuously rotated or rapidly rotated, the bond will be broken. So the energy that has been stored in the bond of the water molecule will be given out in the form of heat. The heat energy produced in such water molecules is sufficient enough to cook food. So a microwave oven is working on the basis of a torque acting on an electric dipole. So as we saw in the earlier heading, that when a dipole is placed in a non-uniform electric field, I can assume minus q1 plus q. What will happen? The force acting on the dipole is not zero. Net force exists on a dipole. So the net force acting on the dipole will make the dipole to rotate rapidly in all directions. Actually, this minus q plus q is nothing but a water molecule. Water molecule behaves as a permanent dipole because their positive and negative charges are kept separated by a finite distance. So they behave as permanent electric dipoles. These permanent electric dipoles are excited by this oscillating torque. What happens? Non-uniform oscillating electric field will make the electric dipole to move randomly and rapidly in all directions. As it tends to rotate in all directions, the bond between the minus and plus q charges gets broken. So the potential energy that has been stored in the bond will be given out in the form of heat, and that heat energy is sufficient enough to cook food. So when the oven is operated, microwaves are generated. Microwaves, which in turn produces non-uniform oscillating electric fields. The water molecules in the food, which are the electric dipoles, permanent electric dipoles, are excited by this oscillating torque. Few bonds in the water molecules get broken, heat energy will be liberated. That heat energy is sufficient enough to cook food. This is the important practical application of the torque acting on an electric dipole in a non-uniform electric field.